Oh, we're recording now. This is lecture 3 in high dimensional probability and data science. Okay. Last class, we started this topic, the big topic of convexity, which plays a huge role, a positive role in the modern data science. Basically, the feeling is that convexity is good and non-convexity is bad. It's non-convexity. Let's say more precisely, convexity is simple. It simplifies problems, and non-convexity is hard. That's a general feeling. So, for example, neural networks are non-convex in some sense, and that's hard. So convexity plays a very, very positive role in modern data science, and we will see a lot of convexity today and later. Specifically, what we did, we introduced for any, let's say, for any set T in Rn, for example, like this, maybe a star or something like this, like that. That's our T. We introduced the convex hull, or in Ukrainian, that would be opukla obolonka, convex hull, denoted simply as CONV of T. And this is the smallest convex set that contains T. So in this particular example, that would be something like that. This hexagon, yeah, it's a hexagon. This would be all of what's inside it is convex hull of T. Analytically, it can be described as the set of all convex combinations of elements of T. And the convex combination is simply, so Z is a convex combination, it's a linear combination. So it's a sum of lambda I Zi, some number of terms. It's a linear combination of elements of T, so Zi are in T. But not all linear combinations. If I allow all linear combinations, it will be the entire space, just entire subspace, infinite in all directions. So these are combinations where lambda i's, the coefficients, have certain restrictions. You think of lambda i's as proportions in which we mix the zi's together. And as proportions, they are positive, non-negative, and they sum to 1. Like percentages in which you mix the zi's. So this is a convex combination like that. Okay, so far so good, remember? Okay, perfect. We initially do not place any restriction on the length of that convex combination, and that can create a problem generally, because, well, it's nice to see that that you can just write like in a basis expansion, but how long? Maybe the complexity is too large. And we proved the approximate Carathéodory theorem that allows you to have very short convex combinations, to shorten convex combinations. So this is what we did. Theorem, approximate Carathéodory theorem, says that let's assume that the diameter of T is less than 1. This is just a scaling restriction because we will measure the error relative to that diameter. So we need to fix some scale. So assume the diameter is less than 1. Then any convex combination, so anything that's in the convex hull, we can even set a budget. We can say, okay, I want to represent it with just k terms. So for any k, I can find points x1 through xk in T, so that I can represent x as an approximate convex combination with this many terms, sum of lambda I xi. But these lambdas are actually all equal. That's an extra feature of approximate Carathéodory theorem. Approximately. So how approximately? The norm, which is just a distance, the usual Euclidean distance in the space, is less than 1 divided by root 2k. Constant 2 is not important. What is important is that this error goes down pretty fast as k goes to infinity, right? So if I have more budget, I want to present it with more terms, then I have a better error. We proved this theorem using probability theory. And the surprise of this theorem is that it is dimension free. Nothing in here, nothing in this theorem depends on the dimension n in which the set lies. Or doesn't even depend on any geometry of T. It's just a fixed error, 1 over root k or something like this. It's beautiful, beautiful result. And that's where we stopped. We proved it and stopped. So that's our last class. Do we have any questions about this before we go to the new material? Good. Okay, perfect. If you have any questions, again, don't hesitate. Just stop me at any time and we'll go over it again. But we're not in any rush. So please do that. Okay, so today we will spend our entire class on applications, of approximate Carathéodory theorem to data science and other areas. So one thing, let me start with a half joke in applications, and then we make it more serious, and you'll understand how it relates to many other problems. So the cocktail problem. So assume that you come into a bar and you have n glasses, different glasses with different cocktails. So you're presented with n glasses of various cocktails that are made. Each cocktail is made of n ingredients in different proportions. For example, I don't know. For example, this is my glass, and one of them glasses, and there are different things here. Maybe there is a gin and rum and juice and a sec, which is French liquor, and so on and so forth. So various ingredients, and they're mixed. There are n of them. There are n such glasses. So let me copy this here. Copy. Another one, and so on and so forth. There's n of them. Okay. What you want to do is you want to make a cocktail with your own proportions by mixing these existing ones. So you want to make a glass of cocktail with the proportions that you want, with given proportions, let's say P1, P2 through Pn. So you have your own idea of a cocktail, your favorite one, and you want to cook your own. How do you do that? There's, say, P1 of gin and P2 of rum and so on and so forth. Pn. So you're given n glasses filled with cocktails and one empty glass, and you would like to mix these glasses in different proportions to make your own. Right? The problem is that there's a lot of restrictions you have to have, right? So you would like to have exact proportion of gin and exact proportion of rum and so on and so forth. How do you make it? Is the problem clear? Is that, yeah. Okay, so why is this about a convex combination? We can think of, let's say, we can look at the amount of gin. Let's say there is Z1 grams of gin here, Z2, and so on, and Zn in the first glass. And in the second, well, it's the first glass, let's say G11, G21, Gn1. In the second glass, G21, Z22, Zn2, and so on and so forth. So we have vectors. Each glass, the composition of each cocktail is a vector. We can encode it as a vector, let's say Z1, Z2, and so on and so forth. And the target cocktail is also a vector. Let's go to P. So we have capital N glasses, we have capital N vectors, Z1, Z2 through Zn, and we would like to cook a given vector P out of them with a lot of restrictions. So we would like, we need, what do we need? We need to find it with the proportions in which the proportion of the first glass, the proportion of the second glass, the proportion of the third glass, and then we mix them on the glass, okay? So we need to find the lambda i's, the proportion of glass I that we'll put in the new glass. Such that what? If we look at each row, like lambda 1 Z11 plus lambda 2 Z21 and so on and so forth equals P1. Right? So we mix all this in these proportions and get exact proportion of gin. And we mix all of these in the same with the same lambdas and get P2 and so on and so forth. And if we write it as a vector, that's going to be just like this: lambda I, Zi. Yeah, clear? In the vector notation, you're just mixing the glasses Zi, cocktails Zi, with proportions lambda I, and you get the new cocktail P. So that's all there is to this equation. And the proportions need to be non-negative because you can't really undo a glass. You have to fill the glass. And they have to sum to 1 because they are proportions, because you're making one glass of it. Good. Yeah. So now this is familiar. This is just a convex combination. So you want to express P as a convex combination of given vectors Zi. You're given vectors Zi, the existing cocktails. You're given a vector P, your preferred cocktail, and you would like to express it as a convex combination. So we exactly have the problem that we are looking at in the convexity context. Good. Clear? Yeah. So this is how we mathematized this problem. Put this in the convexity framework. And when you look at this problem, so lambda, let's see, how do we solve it now? If this wasn't for these restrictions, if there are no restrictions like this, then that would be just what? Just system of linear equations. It's the linear system, P equals 1. So we're looking at lambda i's. Lambda i's are unknowns, so it's a linear system. Well, this is another linear restriction, so there's going to be extra one equation. That's fine, still a linear system. But this is not a linear constraint. It's not like lambda equals 0. Lambda is greater than or equal to 0. That's not a linear constraint. It is a convex constraint, though. And so if you knew a little bit, and I'm not expecting that you do, but if you know a little bit about optimization theory, that is called a. So this is a convex program. For which there are methods to solve it. There are solvers on MATLAB and others, and you can solve it efficiently in theoretical computer science. You say in polynomial time, polynomial, which is good. Polynomial time in the number of glasses n, capital N, and in the number of ingredients, little n. So technically you can do that. But now let's look at the Approximate Carathéodory Theorem and play that theorem instead. Let's resist our temptation to solve it as a convex program and think of Approximate Carathéodory Theorem, which is this. Approximate Carathéodory Theorem says that we have a solution for you. Right? It says you don't even have to compute these proportions lambda I. They're all equal to each other, 1 over k. You just need to know which glasses to mix. You're not mixing all glasses. But the Approximate Carathéodory Theorem says something like, you can stop, don't solve this convex program. We'll just tell you, take cocktail 1, 5, 13, and 17, and mix them in equal proportions. Don't even think, just mix all of them like in proportions 25% each, and you'll get your cocktail approximately. Okay. And that is a much faster and much more elegant, I would say, solution. So Approximate Carathéodory Theorem, it gives us an approximate solution. This is where it is weaker, but where it is stronger is that it only requires few glasses, not all of them will be used. As you can see, you can even you can make a solution with any number of glasses. I say, okay, I just want to mix 3 glasses in optimal. So whatever number of glasses you want, few glasses, and the number of glasses is actually independent regardless of capital N and little n, which is surprising. You're given a lot of glasses and a lot of ingredients, and you want to mix them all. And the solution is, okay, it doesn't matter how many glasses, how many ingredients. Complexity will be the same. Very surprising. And it is fast. It's a fast randomized algorithm that's behind the theorem. The theorem itself that we stated only guarantees the existence. But remember, if we remember how we proved it, it was a randomized algorithm. It was a sampling algorithm. And you can just make the proof into an algorithm, and that just works. And also, additionally, it gives you the same equal proportions, lambda I. Just tell you which glasses to mix, and all this. Okay.
But here also, there is no guarantee that P is in the convex hull. So that algorithm works in that case and says that there is no solution.
Right. Yeah, that's a great question. So for the Approximate Carathéodory Theorem to hold, we need to start with something in the convex hull. So we need to make sure that our target, our desired cocktail, before we solve this problem, we have to make sure that this desired cocktail is in the convex hull of the existing ones. And in fact, it is a necessary condition. If you think about it, it's a necessary condition. If if your desired proportions are out of the convex hull, you cannot mix these glasses. You will never be able to make that cocktail for yourself. So that's a very important observation, is that sometimes this doesn't work, and it doesn't work for a reason. Where it doesn't work, nothing can work. So you can just, there are no proportions, there's no way for you to mix this cocktail at all.
May I ask a question?
Yes, Evgeny, go ahead.
Speaking about this, algorithm based on the Approximate Carathéodory Theorem. As I remember, to implement it, we need to start with some finite representation of this point P. To know what probabilities take, we need some representation of P using these i's.
Yeah, you're right.
So we anyway need to.
Oh yeah. You're right. Yes, forget that. Let's see. Let me go back to this. This is a proof of Approximate Carathéodory Theorem, and how we proved it. We started with some convex combination, and we improved it. Right, so we made this lambda i's the same, and we shortened this convex combination. That's how it works. Approximate Carathéodory Theorem, the proof works by improving the convex combination, but you have to have that. You have to have that in order to improve it. So that's what Evgeny is saying. Yeah, and that is correct. So maybe I should take this. I should make this less optimistic. Yes. I don't think that was, where is it? Sorry. So we're back. So it is not so much a fast randomized algorithm. Yeah. This one. So what you have to do is you still have to solve the convex problem first, I think, to make that convex combination. And then you can improve it. And after you improve it, you have a few number of glasses and you mix it in equal proportions. So maybe let's make an important correction. Approximate Carathéodory Theorem improves this solution, or transforms this solution into an approximate solution with few glasses, and that does so by a fast randomized algorithm and so on and so forth. So this add-on is a fast randomized algorithm, but you have to solve the convex problem first. In fact, I was thinking, can you avoid doing that at all or not? Okay, something to think about. I don't know the top of my head, but let's think offline. Is there any method for approximate solution that avoids solving the convex problem, the exact convex problem in the first hand? Cool. Okay, glad you asked. Any other questions, observations, suggestions? Good. Okay. Okay, so cocktail problem was a half-joking problem, but really its relevance, we will discuss relevance in two cases to data science. Let me just resize this a little bit. So the relevance of cocktail problem, I just indicate two areas that are important. One is to financial mathematics, financial portfolios. So here the ingredients, instead of gin, rum, juice, and so on and so forth, the ingredients are stocks. Think of them as financial stocks. Microsoft, I don't know, Apple, Google. The glasses, the existing glasses of cocktails, they are mutual funds. Mutual funds is basically a combination of stocks in one bundle that is managed by a financial institution together. and the empty glass that you want to fill is your portfolio. So you would like to have a desired combination of stocks. And let's say you want to build them from existing mutual. You don't want to buy individual stocks because it's more vulnerable, but you want to go to financial institutions and you would like to buy existing mutual funds. So the problem here, the equivalent version of a problem, is to create a desired portfolio with a given combination of assets, with a given combination of stocks from the mutual fund, from the available mutual funds. So how do you make that? And the Approximate Caratheodory Theorem offers you a solution. It says you don't have to combine a lot of stocks. You just have to buy a few of them and mix them in equal proportions. That gives you which ones. Good. So that was relevance 1 to the more serious situations, and relevance 2 is this is a more speculative factor analysis generally. This is more open-ended, but you can think of existing vectors z1 through zn as a dictionary of different factors, and you would like them to explain the behavior, a consumer behavior, animal behavior, etc. This is relevant in economics, in the theory of consumer preferences, consumer behavior. The basic idea, kind of underlying idea of economics, of data science, is that behavior of people, animal behavior, and so on and so forth, the behavior can be explained with very few factors. Right? What we do is not usually at every stage is not determined like by 172 factors. We don't keep that in mind. It's usually explained by 3 or 4 factors. Human behavior is very simple in some sense. It's disappointing, but that's true. That's what big companies like Amazon and Netflix try to do. They try to explain the behavior and predict the behavior of people. What movie will this customer will buy next? Okay, that is based on maybe one of the 3 or maybe 4 factors given together, and that is what we need to explain. So Z is let's say a customer behavior, and these are the factors: the education, the income, and so on and so forth. And so the explanation takes this form: sum of lambda I zi. Where lambda I is the proportion. So you mix these factors into proportion, and so lambda I is let's say the factor I explains lambda I percent, lambda I proportion of the customer behavior. So the solution says, okay, here's how you explain this. And let's say income explains 25% of political preferences. And let's say age explains the next 10% of political preferences, and so on and so forth. So this is what we would like to see. The Approximate Caratheodory Theorem, when it comes into play, what it does, it says, it builds an economical, parsimonious model, a very short model. It says, okay, there's a lot of factors out there, and everything can explain everything, but really there is these 5 that are important, right? So this short number of factors, small number of factors can explain the behavior pretty well, like say 99% of the behavior. So the approximate Carathéodory theorem, it builds a parsimonious model. Parsimonious means like economical, short, something that explains this. Short explanatory model. It's not the best method to do that, but it's one of the methods that's available in the factor analysis. Okay, done. Done with first couple applications of approximate Carathéodory. Any questions? Yeah, we're good. Okay, well, we keep going with applications, and one of the underlying goals, continuing goals of this course, is to get you acclimated in spaces of high dimensions, because that's our world, lives in the high dimensional world. The data lives in it, as we know. I would like you to get more confident around phenomena that happen in high dimensions, because these phenomena are sometimes counterintuitive. And people who design algorithms and who do so based on low dimensional intuition usually tend to underperform, and people who design algorithms based on high dimensional intuition usually overperform. And so that's what we would like you to do. So we, in the road, in this journey toward the high dimensional worlds, one important concept plays a big role. It's called covering numbers. This is one of the tools that happen you to quantify the complexity of high dimensional world. It's a very simple thing. You have an object, you have, let's say, a set, I don't know, maybe like this, maybe set T, and you would like to cover it with round balls, with a copy of a given round ball. Let's say this one, something like this. How many balls you need? That's called the covering number. So, oh, sorry. Okay, so here we go. This is one thing, and how many balls we need in doing so? This is called the covering number of T. So let's compute the covering number of T. Let me try to do this as we speak. We try to cover T with these balls. Let me do my best. Like this. The smallest number of the balls, if I'm very lucky, the smallest number of the balls that need to cover T, okay, fun game, huh? Is called the covering number of T. Okay, I was able to, little under, okay. Maybe someone is more lucky than me. It's me. It's a covering number, and it's denoted by n of T and epsilon, where epsilon is the radius of this ball. So this is epsilon. So in this case, nt epsilon is less than 1, 2, 3, 4, 5, 6, 7, 8. We were able to do this with 8 balls, and the smallest number is called n of T epsilon. Maybe it's even smaller, I'm not sure. Maybe someone can do it with 7. And you can do this. Yeah, go ahead.
Is this number connected with like optimal ball spacking number or something like that? Yeah.
This is, there are two cousins. There's covering number and there's a packing number. You want to, here this game is to cover T with balls. Another game would be to pack the balls inside T. And as we will see, they're almost equivalent to, in high dimensions, they're equivalent to each other. So they are connected, yes.
Okay.
But we will, but we'll skip it for now. We'll skip packing for now. We'll not need it. We'll come to that point later. Yeah, it's a very good question. Yeah. Okay. Is the covering number clear intuitively what it is? Yeah. Okay. So definition. The covering number of a set T in Rn at a given scale epsilon is just the smallest number of the round balls of Euclidean balls of radius epsilon that cover T, needed to cover T. Here's definition, here's example. Yep, clear? No questions, definition? Very good. You can think of covering number n of T epsilon as it's a measure of complexity or size of T, but really complexity is a better word in data science. It's how complicated T is. Maybe you can put it, for now, you can put it in the same area of your brain as other measures of size or complexity, like, I don't know, area, volume, surface area, whatever, I don't know. And there's one more, there's covering numbers. But covering numbers is really about the complexity. How big is T? You would like to simplify it something. In high dimensions, unfortunately, the covering numbers suffer from the curse of the dimensionality, as all other concepts are. So they suffer from the curse of dimensionality. How? Let's just take a ball, just round ball for T, and try to cover this ball with the balls twice smaller. How many balls do we need to do that? Let's say you take this ball like this, and we cover it with balls twice smaller, like this. How many balls do we need? In dimension 2, well, actually, I don't know. In dimension 2, I'm not sure if this is known, if this number is known exactly. But it's not large. Maybe, okay, maybe I'm doing a bad job here, but something like this. I'm sure that I can do this with 7, 10 balls or less. In dimension 3, I will need more balls. And in dimension 4, even more. And they may be a surprising, so I was able to do this with 1, 2, 3, 4, 5, 6, 7, 8. 8 here. But in high dimensions, the surprising thing is that you need exponentially many balls to do that. So the proposition is that if B is the Euclidean ball, is a unit, let's say, unit Euclidean ball, which is radius 1, and I'm trying to cover it with the ball twice smaller, radius 1/2. The notation is this, right? It's how many balls I need. Unfortunately, you need at least 2 to the n balls. So this is exponential. Exponential, not good. We don't like that, but that's why. It's really simple. If you look at the volumes, the proof is just by comparing the volumes. Just let's do it intuitively first. So how much of the volume of the entire ball radius 1, is contained in the ball of radius 1/2. So if you compare the volume of radius 1/2 ball and radius 1 ball, what proportion is it? It's not 1/2, right? It's 1/2 cubed in dimension 3, it's 1/2 fourth. So what is it? Speak up. So what?
To the power of n.
2 to the power, exactly. It's 2 to the power of n. 1/2 to the power. Yeah, exactly. So this little ball, each of these little guys, each of these little balls, they contain volume 1/2 to the n, very, very tiny, compared to this ball. And if you want to cover one by the other, well, of course you need a lot of them, right? So each ball cannot really. Each ball only is cutting very, very tiny portion of the volume. So if you want to cover everything, you need too many of them. Okay, so that's an intuitive idea. Yeah. Okay, let's make it formal. So let's assume we make this covering just like in this picture, in the red picture. So assume B is covered by, let's say, n copies of the smaller ball, of a ball twice smaller, which we denote, let's say, 1/2 B. And then compare the volumes. The volume of B is covered by all of these little balls, perhaps with intersection. And that only increases the right-hand side, right? So it's n times the volume of the covering ball. Yeah, is this clear? The volume of what's covered is smaller than n times the volume of. And this scales like 1/2 to the n times the volume of B. That's how the volume scales. If you shrink something twice, then it scales like twice to the n. And that's it. So that's a proof. Volume B cancels on both sides, and you just rearrange the terms. And from this, you get that n, capital N, is greater than 2 to the n. And that's it. So no matter how you cover, you must always have at least 2 to the n. Good. Any questions? Good. And it's a general phenomenon, unfortunately. Generally, the fact that the ball, the covering number of the ball is exponential, it's not just because the ball is bad or something like this. It's just a general phenomenon. Covering numbers are usually exponential in the dimension n. You can take the cube, for example, and it's going to be the same, or anything else is going to be the same. Okay, are you with me? So far, so good? Perfect, okay. So this is kind of bad news because we don't like exponential and exponentially large in data science. Now, the good news, this is not always happening. And there are very nice examples where covering numbers are actually polynomial. And these examples are polytopes with few vertices. So here's a theorem that will prove. So not always. That's good news. So the theorem, you take P be a polytope, and polytope is like a polyhedron in high dimensions. What's in Ukrainian? It's багатокутник. but in high dimensions, in Rn, like a prism or whatever, in Rn. With
probably багатогранник is
багатогранник.
space, and багатокутник is in two-dimensional space.
Yes, багатогранник, yes, thank you. Багатокутник in R2, багатогранник in R3, and generally this thing is called a polytope. So assume it has few vertices, m vertices. Think of this number as not too large. And for scaling reasons, let's assume that the diameter is less than 1. This is just to fix a scale. And we're covering this, we're trying to cover this polytope as usual with the balls of radius epsilon. How many do you need? Okay, good news, polynomial. Okay, m to the power 1 over 2 epsilon squared. You may not immediately like the expression in the right-hand side, but for any fixed epsilon, this expression is polynomial in M. So for example, if epsilon is 1/10, then M, then you have what? Then you have M over 200, I think. It's a lot, but it's still polynomial.
50. It's 50.
10. 50, yeah, divided by 2, yes, sorry, 50. A little better. Thank you. Yeah. So it is polynomial. So this is a surprising thing, given that the entire ball is, to cover the entire ball, you need exponentially many vertices, and for polytopes, you need polynomially many. We'll try to figure out why this happens on the intuitive level a little bit later. We'll try to, just after the proof, we'll try to find this good intuition for that. But let's prove this first. Is the statement of this theorem clear? Everything is good?
So polytope, does it include the interior or it's only the shell?
It does include the interior, yes. I'm not sure how багатогранник includes the interior or not, but yes, it does include the interior. So things like, I don't know, something like this, for example, that we consider as a polytope, everything that's inside. Any other questions? Okay, all right, let's prove it. Okay, first of all, polytopes need not be convex, but we can make them convex. If I take the convex hull, and I'm drawing this on this here, if this was T and I'm taking the convex hull of P, sorry, this was P, convex hull of P. If you have the polytope and it's not convex, let's make it convex by taking the convex hull. What changes? The number of vertices. What happens with the number of vertices?
Will be smaller.
Yes, it can only be smaller. The diameter, same, I guess. Diameter is the largest distance between any two points. So by taking the convex hull, you can only improve the polytope. You can decrease the number of vertices and make the diameter will not change. And so by this pre-processing, I can always assume that the polytope is convex. So WLOG stands for without loss of generality. Без обмеження общності, як воно буде українською?
Загальності.
Загальності, без обмеження загальності, дякую. Without loss of generality, без обмеження загальності, we can assume that P is convex. Okay, that's first step. Second step. If you take a convex polytope, like this, take a convex polytope P, it is clear, it's a theorem, but it's clear that it is a convex hull of its vertices. Right, I can take this vertices marked in as these dots, and the convex hull of these points will be exactly the polytope. So P equals the convex hull of T, where T is just this discrete set of the vertices of P. Good. Okay, and now we apply Approximate Carathéodory Theorem. Apply Approximate Carathéodory Theorem. It says that any point in P, in the convex hull of T, any point in this polytope. Let me scroll up just to show Approximate Carathéodory Theorem for 1 second. I'm scrolling this up to the first page. And this is the statement. Any set X in the convex hull, which will be in the polytope, is within this distance from the convex hull like this of the vertices. Okay, T is the vertices. Okay, so let's just remember, I'll scroll down now. So any point in the polytope can be represented approximately like this, where xi are the vertices. Let me rewrite it here. Any set in P can be approximately, so is within distance 1/√2k, that's an error in the theorem, from some point like this, 1/k, some k xi, where xi is in T. Some point in this set, let's call it script n, like calligraphic n, like this. Okay, I just wanted to restate Approximate Carathéodory Theorem geometrically. I can approximate any point in the convex hull with this error by this point. That's all I did. Good. Okay, and now let's do this more geometrically. What does it mean that a point is within this distance from the other point? It means that it can be covered by a ball centered right there. Right? So it means that this P is covered by a ball of this radius, centered at some point from the set. Yeah, okay, is it clear? Yeah, X is within distance epsilon from Y if X is covered by the ball centered at Y with the radius epsilon. That's okay, perfect. So what does it mean? Just look, every point, just reread the sentence. Every point in this polytope is covered by a ball centered at the set. So it means that we covered the polytope with these balls. How many of them? As many as the size of the set. That's our covering. We did this covering, and how many points are in N? That's an interesting question. So let's think now. Sorry. So far, so good? this is it's a conceptual proof, and everything is clear so far.
So here we for any vertex we either take it or we don't take it.
You're
But,
thinking about the size, right? Matej, you're thinking about the size now?
Yes, but
Yeah.
I just remembered that we have exactly k of them. So it's
Yeah, exactly. So let's now think how to bound the size. How many points are there in M? What decision do we have to make to fix a point? We need to know which vertices, right? There are k, like you said, there are k. We choose a combination of k vertices and just take them average. And that's what M is.
and we can repeat them. Yes.
Yes, and we can repeat them. So we
Yeah.
choose
Then
k.
it's just we choose k time from M vertices, and it's just M the power of k. We don't even need any binomial.
Exactly. So it's whatever size t is, and this is M, raised to the power k, and this is because this is a number of ways. How do we fix an element in N? We just choose k elements of t. Sorry, not k. K elements from t with repetition, possibly with repetitions. That's basic combinatorics, right? You choose first element in t ways, second element in t ways, times third element in t ways, and generally this number of ways to choose will be.
Sorry, I think there shouldn't be an equation, but rather an inequality, because some points may coincide.
Oh yeah. That's a good point. Inequality, right? Because sometimes they can collapse. Different combinations can average to the same point. Yes. Yeah, that's a good thing. Yep. Anything else? We're good. So that's it. Remember, T was the set of vertices, and we assume there's M vertices. So this is M to the K. Perfect. So that's basically our result. So now we just make this to be epsilon. Just change notation. If this is epsilon, then K will be just if epsilon is 1√2k, then K is 1/2 epsilon squared, I believe. And that's it. So then we finish the proof. That's what we wanted to show. Good. Any questions? Good. When I looked first at this result, when I don't know, it's your age, I couldn't believe it, because it's, I don't know. Look at this, for example. You have a polytope. And let's say this is a ball, B, Euclidean ball. And we know we cannot cover B. To cover B with these balls, we need exponentially many of them. And to cover P, we need polynomially many. So this means that this polytope P here inside, it really takes a very, very tiny space, a tiny room in the ball. So this picture is wrong. In 2 dimensions, it's clear that's there. And in 2 dimensions, it doesn't really, how much larger B is compared to P? Well, maybe twice, I don't know, 1.5 larger. And so if we can cover P with polynomially many, we just cover it a little bit around it, and we get the covering of B with polynomially many. But in high dimensions, that's not true, right? The complexity of B, the number of balls to need to cover B is exponential, and the cover of balls to need to cover P is polynomial. which is much, much smaller. How can this be? So this means that this picture is kind of misleading. Our two-dimensional intuition is misleading. And one of the goals of this course is to get you to a better intuition. To actually, we'll redraw this picture. When we think about polytopes in high dimensions, we don't think about this picture anymore. I'll show you. This is very intriguing, but I'll show you the kind of a hyperbolic correction to the intuition in high dimensions, which really is helping in geometry and the data science in particular. So we'll do it next.
I have a question.
Mhm.
When we were covering the ball, it is exponential in terms of dimension, right? But this expression for the polytope it does not depend on n at all, and we are in r times n, r to the power of n. So it's you were saying that in one case it's exponential, in the other it's polynomial, but there are exponential and polynomial for different variables, right?
Yeah, that's right. Okay, yeah, I should correct myself. You're right. I'm comparing apples and oranges. There is n and there is m, and I'm just putting the same scale. Let's think about this way. Let's think about polytopes that have non-empty interior, not just flat polytopes, but polytopes with some non-empty interior. In that case, the number of vertices must be at least n. The number of vertices must be at least the same as the dimension, I believe, right? Even n plus 1, I think.
N plus 1.
Even n plus 1, yeah, but yeah, let's forget one. So this m is even larger than the dimension. And yet we have this bound, which is polynomial in capital M. I see what you mean. So yeah. So okay, sorry, wrong direction. So let's say M is, just to make a fair comparison, let's make M equals 10n. We have a polytope with 10n vertices, let's say. So you can build a polytope with 10n vertices in high dimensions. It's a pretty good polytope. Then there is a fair comparison. So it will be still polynomial in n in the dimension. Of course, what you can say, and that is actually a good point. So of course, what you can say is that, well, if all of my argument, what goes wrong if n is exponential in n itself, if we have a polytope with too many vertices, extremely many, exponentially many vertices, then it invalidates all this contradiction, because the right-hand side here will again be exponential in dimension, just like in the ball. And that's a fact of life. Because eventually, if you have the ball, you can approximate it with polytopes. If you have an unrestricted number of vertices, then you will just pick them very, very densely on the ball, and your polytope will be indistinguishable basically from the ball. Just a regular polygon that converges to the circle in the same sense. This will converge, and then we should not see any difference in the covering numbers, which is true. You can approximate a ball with a polytope. That's true, and in dimension 2, remember how in dimension 2 you approximate the circle. I can't remember, it was Plateau probably who first did it. First it's triangle, and then the square, and then the pentagon, and then a hexagon, and so on and so forth. And these regular polygons converge to the circle, and they converge at linear rate. So if m is about the same as n, sorry, if the number of vertices increases, then the quality of convergence is linear. So just the the gap between the circle and the polygon decreases pretty fast linearly, maybe even faster than linear. Not so in high dimensions. In high dimensions, you need exponentially many vertices before you can see any meaningful approximation. Right? So to approximate the unit ball with a polytope, you need polytopes of extremely large complexity. You need polytopes with exponentially many vertices. And that is also the context of this thing. If you have that, then. Which is again a surprise. Why would that be true? I don't know.
Can I ask you a question?
Yeah.
Would it be more appropriate to actually evaluate, say, you start with the square in R2, then you go to cube, R3, and then you go to a higher dimensional cube, and then you would get an exponential rate. And what I wanted to pinpoint is if you compare the cube and the pyramid with four vertices, the cube with the same diameter, it seems to be quite larger than the pyramid. So
Yeah.
Even in the volume.
Exactly. I think so too. Yeah, this that's a great remark. I think this theorem is useless for the cube, and why so? Is you said it yourself. If we have the cube, if you have the cube like this, hypercube in high dimensions, like this, then how many vertices does it have? Well, in dimension 3 it has 8. Dimension 2 it has 4. In dimension 3 it has 8. And in dimension n, it has 2 to the n vertices. So the number of vertices is exponentially large in dimension. And so this theorem it's not really helping. To cover the cube, for example, you'd be just better off embedding cube in the ball and covering the ball. And you will see the same exponential number of balls needed. So the cube is kind of a bad example for here, and for a reason. The cube itself. Let me actually tell you an interesting story about the cube. The cube itself does not approximate the ball really well. Well, only at the endpoints. Let's say I take the outer, the exterior sphere. So the endpoints touch the sphere, but the faces are too far. So if you look, for example, at if you walk from the middle toward the face and then to the sphere, this distance will be, let me think. I think it will be 1 divided by root n compared to this. So the faces are too deep. So the ball does not approximate, the cube does not well approximate the unit ball. But I think the following is true. This is a very deep theorem. There are 2 theorems actually. Theorem 1, you take the cube, you take 2 cubes, one original one, and the other is a rotated copy, random rotation. So you just randomly rotate the cube and take the convex hull. So I don't know how to draw in 3 dimensions, but let's say in 2. So take the cube, randomly rotate it, and then take the convex hull. So this thing will approximate the unit, the Euclidean, the round ball very nicely. This will be a good approximation. So although the cube itself, it's not really a good approximation, the 2 cubes already are. And another theorem. You take the cube and randomly project it. Just rotate and project it somehow onto a plane of dimension, let's say n/2. Space of dimension n/2. The result is some complicated polytope, but that polytope will approximate the ball. So that will be a very good approximation already. So what I'm saying is that the cube itself is almost like the ball. Not immediately, but with some post-processing. Either you do 2 cubes or you project it or something like this. There is very little that's needed to make a ball out of a cube. The cube is almost like a ball. And that is manifested in this theorem too. The cube has exponentially many vertices. And so if you apply it to here, you will not see any difference from the ball. It will be the same exponential covering number. What the theorem is good for example, is a simplex. Simplex, you know what simplex is? Okay, maybe we should just say one thing. So simplex, you just take coordinate vectors in Rn, 1, 1, 1, and you take their convex hull. So this is a unit simplex. This unit simplex you re-embed in R2. It's this flat thing. So, and in Rn you have the same. It's in R3. It's a I can't remember, tetrahedron. That's what it's called, I think. Tetrahedron and so on. So the simplex has very few vertices. It has n vertices. Actually, n+1 vertices in Rn. And that is where the theorem applies very well. For here m equals n+1, and so there is no difference, and therefore the simplex has a very, very small covering number, polynomially covering number, which is surprising too. I don't know what to think about it, but it's like you can cover this with, of course I can cover n vertices, but how do you fill the spaces between them, and why only few balls needed to do that? I don't know, other than from this theorem. Okay, guys, any other questions about this? No? Good, we'll stop recording now.